So thank you all for being here. I'm going to jump right in and just kind of tell you why I think roots are important. So when I left undergrad, I went and worked at this site, the Duke Face site in the southeastern US for a couple years. And the two things that I learned, the first was that roots are important. And I say that because at this site and also at the Oak Ridge Face site and a lot of our other whole ecosystem studies, I think we weren't able to really interpret the responses of these ecosystems without actually thinking about what was happening below ground, whether that was specifically a root response or simply a mineral nutrient limitation, which I would argue is going to be mediated at some level through root response. It's that below ground story that I think is important. The second piece I learned was that roots are frustrating and we're way behind in what we understand and know, which I will view as an opportunity. But that's going to be some of what we talk about today, is sort of revisiting some of our basic assumptions that we've taken maybe from leaves above ground and trying to reinterpret them from a root perspective, or I'll say more broadly from a below ground perspective. So thinking about root traits and how we can take this to an ecosystem, I actually want to go way back and ask two very, very simple questions that will frame this talk. The first is, what are fine roots? This is not what are traits. But yeah, it is, in that sense, it's a very simple question that I think has a lot of meaning as far as what our answer is. And the second is, what are acquisitive fine roots? Now, when I say what are fine roots, I'm thinking about within a single root system, even within a single branch, what's going on there, what should we consider a fine root, and should we think about the diversity at very, very small scales in that branch, or can we sort of lump things together? And then when I think what are acquisitive fine roots, or thinking about a trait spectrum, I'm really thinking about how we compare different plant systems. So thinking about how root systems might vary across different species or potentially change within a species. But this is really a question of comparing across. So the take-home message, in case roots become too difficult to follow, is that if we want to link roots to ecosystem processes, and I think if we want to really then understand our ecosystem processes, it requires understanding functional heterogeneity among fine roots, and it requires understanding, and as much as we can, accounting for trade-offs with mycorrhizal fungi, so these symbiotic fungi that associate with the roots of not all, but many of our land plants. So the first question, what are fine roots? So that has been answered for decades, centuries really. It's generally everything below some type of diameter cutoff. Most recently, for the last several decades, we've more or less coalesced on less than 2 millimeters being a fine root. But if you look down into this branch, I'm going to point out this branch here, pretty much everything is less than 2 millimeters. But we can actually break this down to be a lot more specific. One of the ways we do that is with an ordering-based system. So this is like a stream order that we use to count river streams as they merge together. So our most distal roots are this first order here, and where it branches together. So you have this first order, and it comes into this longer one. That's a second order. Where those come together is a third order and a fourth order and higher up. There are many different ways to do that, but this is how I'm going to do it here. When you actually compare these different root orders, there's a tremendous diversity, both in form and function, below this 2 millimeter cutoff. So this is just looking at root anatomy, some cross sections across 5 different orders. This is a maple species here. So when you're most distal, the thinnest root order, there's very little secondary development, intact cortex, there's very little steel development. So these roots tend to have high capacity for radial movement of water and nutrients into the root, but they don't have really great steel or xylem, so they can't actually move very efficiently up the roots. But as you go to a higher order root, like this fourth order root or fifth order root, they've lost all the outer cortex, which is where you have good influx of water. But instead, they've replaced that with really well-developed xylem. So the capacity for moving water and nutrients axially in that system is greatly increased. And this anatomical change across root order is then associated, coincidentally or because of some type of physical trade-off, with a whole suite of changes across these root orders. So I'm talking about root orders here on the x-axis. So this first order root has high capacity for water influx radially. That declines as you move into this higher order root. Respiration rate tends to decline as you move to higher order roots. Whereas transport capacity, how long the roots live, the chemistry of the roots, these are all changing dramatically across these, within a system, but across these different root orders. And you can simplify that and just say uptake capacity declines, transport capacity increases, respiration rate declines, metabolic activity declines, lifespan is going to increase, nitrogen concentration declines, whereas a whole slew of other chemical constituents of the roots tends to increase. So despite this well-documented and generally pretty predictable variation across root orders, we tend to lump all of this into one single pool and say, these are fine roots, they do the same thing, and they have the same function, which I think is increasingly not fair and is not going to get us the answer and the understanding that we need in an ecosystem. So one of the things I'm going to argue for today is breaking this into two pools. I will say in an ideal world, we're going to break this into individual root orders, but if you're taking 50 soil cores to do an ecosystem level assessment of biomass, you're not going to dissect all those roots into individual root orders. So we need a tractable way of actually honing in on functions. So that's what we actually want to do here, is basically try to identify the pool of roots that basically serve the function for uptake, and try to identify the pool of roots that serve a basic function for transport, also serve as the framework for that distal root system. So we can do this, but the next question is, just because we can do it, does it actually enhance or improve our understanding of an ecosystem process? Which we will get to. So again, we're going to move from this traditional approach to order-based when you can, but then doing something like the functional classification. So does that make a difference? And I want to ask that with a case study here. So this is changing from a one pool to a two pool model. So again, a fairly tractable change. Does it actually matter? So I'm going to do a case study here. We're going to compare estimates of global NPP that would be allocated to fine roots. So a fairly big scale estimate, and to do that we need three basic pieces of data. One is standing fine root biomass. The second is turnover rate, so how fast does that root pool need to be replaced for each fine root pool. And then if we have that biomass, which based on most of our older studies, so most of our data that we have available, it's going to be on a pool of less than 2 millimeters. How do I allocate that into smaller pools of absorptive and transport roots? So we find these three pieces of data. The first, we're going to take our fine root biomass across global biomes, comes from this classic paper, Jackson, Mooney, and Schultz in '97. And we use this for two reasons. One, because it gives us ready-made data for root biomass across the globe and different biomes. Two is because this paper basically gave us the benchmark against which we compare all of our root estimates now. So if you do an ecosystem or even just a plant level study, and I want to estimate how much NPP do I think is being allocated to that root system, and I come up with a percent estimate, I tend to reference, oh, so that was about the same as what Jackson, Mooney, and Schultz found, or it was a little bit more or a little bit less. So it gave us a really good benchmark to compare our data to. So for the second part, we need to know turnover rate. So Jackson, Mooney, and Schultz assumed that all roots turn over once per year. So that means they have a lifespan of about 1 year. Once per year, that entire fine root system is replaced. We kept that for absorptive roots, which I think is a fair starting point. There's certainly a lot of variation there. There's many roots that turn over faster, many roots that turn over slower, but this is a fine starting point. But the key difference was with transport roots. So these roots that we know live much longer. In this case, we used an estimate of a lifespan of 10 years, which means they're replaced, 0.1 of the population is replaced each year. And we use this number. So we actually do several numbers. So a lot of this analysis is in a paper that was published in New Phytologist in 2015, where we used another number that we can talk about later. But for today, I'll just show this one. And then the last piece is biomass partitioning estimates among fine roots. So this is the real uncertainty, I think, in our analysis so far. We know these traits differ. We know the difference in turnover rates is a pretty fair starting point. We don't necessarily know, have great numbers on how to allocate that 2 millimeter pool into two separate biomass pools. So we did the best we could, started with about 20 species that were published in the literature that actually had separated biomass by some anatomical difference, or actually done it for each individual root order. We ended up having about 20 different species or sites. This did include herbaceous and woody species across about 5 different biomes, so we do have global coverage in that sense. We just don't have deep global coverage, but it's a good place to start. But it's also a great place to do some more work if you want to measure some roots and actually beef up our numbers here. I'd love to see that. So the proportion that we allocated to absorptive roots varied by the biome type. We just simplified it into a woody biome, so not surprisingly between woody and herbaceous, we found that herbaceous tend to have a lot more of their roots in this absorptive class, Many herbaceous plants have nothing but absorptive roots, no secondary development. They're not turning over slowly. But there were some herbaceous plants that would actually persist for multiple years, and so we did actually have many that had a longer-lived root class. Whereas woody, most of it is in this transport group. And then annual croplands, we made the assumption that if that cropland is plowed over at the end of the year, there's no way roots are persisting for more than 1 year. And so the results that we had are, again, starting with Jackson's number of 33%. This is saying all fine roots turn over once per year across the globe. If we split that into functional pools of fine roots, we bump that number down to about 20%. And again, this is based simply on well-known trait differences across these species that we can use to inform, or at least I'll say constrainer estimate, 33% is probably on the high end. Now again, I said we did have a lot of uncertainty in our allocation of an absorptive fine root pool versus a transport fine root pool. So if we look on the very high end of absorptive fine roots, that number is more like 28%. If we look on the very low end of absorptive fine roots, where most roots are this transport group, based on what we saw across our 20 species that we had, that number actually gets bumped all the way down to about 13%. So there's a lot of uncertainty just on the few studies that we have. But in any case, I think this is the most fair starting point that we've actually reduced our global estimate by about 1/3 for how much you need to replace a standing fine root pool on an annual basis. Now again, I did this at the global scale. It doesn't matter if you're doing this at the global scale or at the level of an individual plant. The same principles hold, and so we actually did the same analysis. So this is a longleaf pine ecosystem here in southeast United States, where they'd previously done some assessments on root biomass and estimated that probably about 18% of NPP in that specific ecosystem should go to fine root turnover. If we actually partition that into a longer-lived fine root pool and a shorter-lived fine root pool, that bumps down to about 11%. So again, we're seeing a consistent reduction, which is what you'd expect. But that works at all different scales. So I think this is relevant to any study that's looking at where's NPP going in your ecosystem. So on the whole, using a two-pool model substantially reduced estimates of NPP allocation going to fine roots by about 1/3. I do want to mention that I don't think there's not as much NPP going below ground. I just think we haven't really constrained our estimates very well before, so we've been able to conveniently ignore things like exudates, mycorrhizal fungi. I'm not saying we've ignored respiration, but we certainly haven't been able to constrain these things very well. So while this is a good estimate on its own, I think it also gives us the power to constrain this and look where this carbon might be going somewhere else, probably below ground. That is my bias, though, I'll admit. So what are fine roots? They're a heterogeneous pool of roots that diverge in their capacity for resource absorption and transport. It's not a sexy definition, but I think it's more accurate than everything less than 2 millimeters. And in general, I think the functional approach gives us a tractable way to actually account for that, particularly if you're working at an ecosystem scale. If you can do something at a smaller scale, if you really want to compare root traits at the species level, I would advocate for something like an order-based approach as being more precise. So the second main question I wanted to talk about is, what are acquisitive roots? And I'm thinking about this whole acquisitive versus conservative spectrum, or fast, slow. And so revisiting some of what Peter talked about today, if we think about acquisitive versus conservative, I think the way that I first learned it or thought about it is to think about a leaf, which in this case I'm saying same mass, so it's Peter's same piece of paper, which actually meant to borrow that for this talk. I'm sorry, but I'll use it next time. So if you have a thin leaf, you could get a lot more surface area than if you have a thick leaf. So when we think about that, it's sort of a trade-off between the acquisitive capacity and the leaf mass per area, which we know is wrapped up in a whole bunch of other things with other trade-offs that we've found or sometimes don't find between lifespan, nitrogen, and LMA. Gives you that acquisitive capacity and ultimately your total return on investment. So what we've been doing in the root world for, I think, the past 10 years is then stealing all the ideas that have been really well developed above ground and applying those downstairs. So what should be our defining root traits for acquisition? What we've generally been doing is saying, okay, well, if you have thin-rooted species like this species on the left, that's probably more acquisitive, so you tend to have high specific root length. Whereas if you have thick-rooted species like this one on the right, tend to have low specific root length, and that sort of defined our acquisitive to conservative spectrum in roots. But that completely ignores mycorrhizal fungi. So again, these are the symbiotic fungi that associate with roots in most of our terrestrial ecosystems. I think Etienne will talk about a pretty cool ecosystem that has a high proportion of non-mycorrhizal species. So they are super important globally to think about just roots alone, but also globally, I think the vast majority of our species, we have to think about mycorrhizal fungi. So this is going back to the first place I worked again. These are roots from the Duke Face site in southeastern United States. These are pine roots here with this nice bright red. These are ectomycorrhizas branching off the pine root, and then all this white out in the soil is the mycorrhizal hyphae. So if you get the impression from, or I hope you get the impression from this, that there's a tremendous amount of surface area built up by these mycorrhizal hyphae that ostensibly are returning nutrients from the soil to the plant in exchange for carbohydrates. So you can think about it as an extension of that root network, though I will acknowledge that is a root-centric perspective. Something else that's important that we know across roots and root morphology with mycorrhizal fungi, typically small diameter roots have lower colonization than large diameter roots. Now I will point out that it's really not a linear relationship. Basically, large diameter roots almost invariably have low colonization. It just doesn't seem to be a functional strategy. Whereas small diameter roots, you have many species with low mycorrhizal colonization and many species with high mycorrhizal colonization. So keep that in the back of your mind. So are thin roots more acquisitive and are thick roots more conservative? That's the basic question to address here. So to do this, I want to share a heuristic model that's going to test that assumption and say, do thin roots have greater surface area per unit mass than thick roots? So that's going to be our defining feature, surface area per unit mass. So basically specific root area, but not just roots anymore, specific root and mycorrhizal surface area. And then look at some of the basic patterns that we expect to find if we have a clean acquisitive to conservative spectrum and find roots. Look at some of these patterns that we'd expect at a global scale using a recently released root trait database. So this first piece, surface area per unit mass. I'm going to start with defining archetypes for this heuristic model. So again, it's a very simple way of showing this. But across this range, each one of these dots basically pins a root type that I wanted to look at in this model. So basically we have thick roots with high colonization, thin roots with low colonization, medium-sized roots with medium amounts of colonization. And then within this, I also am varying the density of those roots. So I'm not showing it here because 3-axis panels, I'm not good at those. But on the whole, we also have root density that is varying quite a bit across some of these species. So density is also going to define the amount of mass you invest per unit surface area. So the roots look like this. We have, again, diameter. This is basically, these traits I'm going to show here are very simple, and that's basically what the model is built on. So it is very simple. Diameter is declining across these. So again, we have a variation, so similar diameters here, but really high colonization with this one, whereas sort of average colonization with the other species. And then a thin root that is relatively dense versus a thin root that is more, we'll say, flimsy or has low density. And then, so again, looking at this density, specific root length, and then varying this mycorrhizal colonization across those 6 root archetypes. So based on that information that we give it, and then we add on top of that the diameter of mycorrhizal hyphae, and then the likely amount of surface area you would have in the soil based on that amount of mycorrhizal hyphae, and how much hyphae we tend to see associated for a given unit of root mass that is colonized. So that gets messy, but basically we're taking roots and we're adding the hyphae on top of it, so we'll have hyphal length, hyphal diameter, hyphal density, just like we have root density and root diameter, but we're adding a certain amount on top of it based on how colonized they are. So species with 90% colonization will get a lot more hyphal mass associated, whereas the species with 10% will have very little, mostly just be relying on the root itself. So again, this assessment is based on just surface area per unit mass. There is a ton of other information that I think is important that we're going to ignore today. That's why it's a heuristic model, but I'd love to have conversations about that later. So what do we expect on the whole in this fast, slow, acquisitive, conservative? Thick roots should have low surface area, be much more conservative. Thin roots should have relatively high surface area. So if we look at just the root, that's generally what we get. Thin roots have really high surface area per unit mass. Thick roots have much lower. There's a little dip down here because this one has a lot of density, so this is intuitive. What I want to point out before we move to the next one is this unit here is about 60 millimeters square per milligram of mass invested. When you add in what you'd expect to find if you account for mycorrhizal fungi, that bumps up to about 300. So what I want to immediately point out is actually accounting for the surface area that you get from mycorrhizal fungi in some cases can dwarf what you're getting from the root by itself. The second thing to point out is, at least in this case with roots and 3 micron diameter hyphae, you do tend to get sort of the directional response, with thin roots being more acquisitive, thick roots being quite unacquisitive. If you assume a 10 micron diameter hyphae, that levels out quite a bit more. The reason I did 3 and 10 is basically we have very, very poor information constraining this, and 3 and 10 were the high and low values that I found for typical mycorrhizal hyphae diameter, but we can, I think, do a much better job of that with some targeted sampling. So the first piece, or the piece here is, it levels out somewhat at the top. I'm not going to pretend like this guy's not still lagging behind, but across the medium, thin, dense, it's more of an equal ball game. Now, this was assuming a high amount of hyphae per unit colonized root. So actually, I'll just put it out here and say this is assuming you get about 10 meters of hyphae per centimeter of colonized root. I'm going to show you an example with a much lower amount of hyphae per centimeter colonized root in a second. But I did want to throw this in just to point out, so here's a non-mycorrhizal root archetype that I added. So again, you get no benefit from mycorrhizal fungi, but they tend to be very, very thin, tend to have very low density. So by itself, this is the root alone is doing a lot, but still doesn't seem to compensate for mycorrhizal fungi in some cases. But if we go from high amount of fungi per unit root to a low amount of fungi per unit root, so this was, again, high hyphal production was 10 meters per centimeter of root. This one is going down to 1 meter per centimeter of root. Again, that's a huge range because in the literature I find a huge range. We get a very different story. This is generally more equivocal across the different root types. 2, you'll notice that all of a sudden non-mycorrhizal species seem to be a very acquisitive, and I might even argue very efficient strategy. But my take home from that is not that mycorrhizal fungi aren't the best option, but that our parameters constraining mycorrhizal fungi are ridiculously poor, which is what I think results in the incredible spread that I have across these 4 panels. So on the whole, are thin roots more acquisitive? I definitely think sometimes, but not always. Results can be equivocal depending on the assumed hyphal diameter and on the amount of hyphal production. So changing assumptions about the hyphae that we used, I think, fundamentally changes how I interpreted this model. So day 1, I do hyphae with high production, and I have a clean story. And then day 2, I do a lower hyphal production, and now I have no idea what my story is, other than to say that we need much better estimates for mycorrhizal hyphae, but I think we can't interpret root strategies without that. But if we were going to do that and just look at root traits alone at a global scale, which I think is still quite useful, starting with sort of the trio of traits that I often look at above ground, lifespan, nitrogen, and LMA, and switch this to root lifespan, root nitrogen, and root diameter, or SRL, what patterns would we expect to find? So again, we're using a global fine root trait database, lovingly called FRED. So I won't talk a whole lot about this given time, but I would love to talk more about it later if anyone's interested. But all of this is also uploaded into Try, so Jens might say the word FRED, and that's our FRED. That has been a great effort between Colleen Iverson, who's not here, but Jens and Catherine and Peter and others, so thanks to that whole group. Do we observe meaningful relationships in these core traits? The first I'm going to show are lifespan. Now, I showed a global map, and then I come up with sample sizes of 30 and 33. I did constrain this to basically estimates that I had confidence in, i.e. we're done with a method. So observing root lifespan is a mess and a hassle. And so when you actually try to limit it to equivocal measures of root lifespan, we all of a sudden bump down to 33. But across these 33 species, which are global in that it's not just from one site, we do have patterns with first order root lifespan or root nitrogen. Higher nitrogen tends to be associated with a lower lifespan. Here, higher diameter tends to be associated with higher root lifespan, so that makes sense. It pretty much reflects what we often see in leaves above ground. But if we want to look at this nitrogen to diameter trade-off, which is the one I was more interested in because the one I really didn't know what the answer would be, we don't see much of a relationship. They're largely decoupled, so basically you can have thick and thin roots with high and low nitrogen, which isn't terribly surprising. So can we learn from approaches above ground? I say this and I throw this out now because I'd love to have you all tell me what we can do better later. In the sense that I think there's been a tremendous amount of really, really savvy analyses that have gone on in the past decade, several decades, that there's no reason we need to do it over again and figure out a new approach. I think you all have nice ways of doing it, so I think we can learn a lot from that. But explicitly incorporating mycorrhizal fungi into this story, I think it's an open question if they will help us answer this and help us understand some of the trait decouplings that we see across different environments, or it's entirely possible they'll just make it a bigger mess, which I'm okay with because that's an opportunity to sift through that mess and learn a more interesting story. So are thin roots more acquisitive? I'm going to say it's more nuanced, to say the least. I do think there are relationships there that will be meaningful. But at a minimum, it's complicated by mycorrhizal fungi and independence among core traits. So my summary here is, I think a functional tuple approach, when you're doing your root assessments at an ecosystem scale, I think we have to start doing this or something like this. Again, order-based is great, but we can't do it all the time. So something like this is at least going to get us in I think, a more constrained arena than just a 2 millimeter classification alone. And then root traits on the whole, I think our concepts of how they relate across species is quite fuzzy when you think about mycorrhizal fungi. So my not so subliminal message here at the bottom is every aspect of root function will be altered by mycorrhizal fungi. The ... is me adding in, and probably other symbiotic bacteria, things in the rhizosphere, everything that happens in soil. So it's a huge mess, but I think that means it's a huge opportunity. And while I don't think we could have done it 10 years ago, I think today there's not a huge reason to not explicitly think about mycorrhizal fungi. We have the tools to do a much better job, and I think that will give us a much better understanding of our ecosystems as a result. So tremendous thanks to the organizers and to New Phytologist, and I will leave that up on the screen if you have any questions about anything in the talk or want to talk to me about Fred afterwards. Thank you very much.